Welcome to Unlocking Direct Current in Buildings, why it matters, how to implement it, and what's next with Current OS. We are thrilled to have you join us today. Our hosts are Mame-Thiedel Thiongane, who is project manager from Cegelec Vinci Energies, Adam Selvey, who is head of engineering, design, and innovation for the built environment from Jacobs. We have Giel van den Broeck, who is co-founder and CTO of Direct Energy Partner, and Avinash Papisetti, who is DC Global Business Development Manager from Schneider Electric. They are all valued partners of Current OS. And from Current OS, we also have Prashant Kurup, who is the General Secretary, and I am Raphael Raymond, responsible for marketing activities of Current OS. Before we dive in, I have a few housekeeping notes for you. Feel free to ask any questions in the chat. So we have set aside plenty of time after the presentation to address your questions and have a discussion. The webinar is being recorded, so you will receive a link via email. You can also access it on the LinkedIn event page where you're registered. And of course, we are happy if you follow us on LinkedIn or YouTube. It's a great way to stay connected with our vibrant DC community. I'll start with a few words about Current OS for those of you who don't know us. We are a non-profit organization defining standards for direct current microgrids. We want to ensure reliable and sustainable power distribution in buildings and installations. Current OS standardization efforts are conducted in coordination with the IEC, the International Electrotechnical Commission, and we are a liaison A status with the SIC LVDC, the System Committee for Low Voltage Direct Current. Today we have 75 partners. It's growing every week across 25 countries in North America, in Europe, in Asia. So this is really a growing community of DC fans. What do these DC partners do? This ecosystem of partners, they are actually in very various departments and industries linked to buildings. They cover different types of devices, equipment, and what they are doing together is to support real-world DC implementation, real-world project and installations. These pioneer installations really showcase the benefit of DC with Current OS rules in practice. So examples include office buildings, EV charging parks, university campuses, data centers, street lightings, just to name a few. This collaborative partnership welcomes all stakeholders. So you are welcome to join us, to contact us for questions. We want to make the energy transition, a reality in the building industry. And we are especially looking to collaborate with loan manufacturers, design consultants, integrators, architects, real estate investors, insurance companies, you name it. If you are interested in joining the conversation, this is how to reach to us. Now, without further ado, over to our hosts, Avinash and Adam. The floor is yours to begin. Where would you like to start?
Hello and thank you, Raphael. Welcome everyone. So we thought of making it like a Q&A session, and thanks for this introduction, Raphael. So the theme of this the entire conversation about how we can create a differentiation, especially on the buildings. You know, when it comes to the topic of buildings, the one of the questions that pops into the mind is like, yeah, how can I even start with the design? Or wherein it brings the importance of the awareness of the design firms. And thanks to the likes of Adam, where they're steering from the front, the topic of DC for the design firms. So here is my question to Adam. Adam, what do you think on your perspective? Why is direct current the future of building design?
Thank you, Avinash. So if we go to the next slide and kind of just really to reiterate something. The next slide. So this is the opening topic and the opening kind of gambit of everything, to say that conventional thinking is that Tesla won the war of the currents. So if you look at most textbooks, you look at most things, it says Edison failed in his quest for DC. I know we were having a debate the other day about some people get confused sometimes because Tesla is the name of the car. And Musk decided to kind of coin it from a DC perspective in cars. So everyone automatically kind of psychologically now thinks it was Tesla that was DC, but no, that was Edison. So Tesla won it in the 1896 when he had Niagara Falls power plant. And then everyone thought, that's great, we all want an AC future, and we're all ploughing around now. Even today, we're designing multiple buildings with AC networks. But since 1950 and the advent of electronics, consumer electronics, power electronics, we have just literally created Edison's world. Yeah. So we thought we were in an AC world, and we've created loads of DC products. And those DC products obviously then all need conversion to actually work. So as soon as you start to do this, yeah, you've got this whole DC world that's actually being connected, and there's loads of inefficiencies. So the first thing is we are already in a DC world. We just happen to connect it to an AC Tesla network. Yeah. So if we then go to the next, and as you say, you can see that through things like the Paris Agreement and climate change and sustainability, DC is the future for us to actually get to the point of where we actually want to be from a sustainability perspective. And we've got obviously current OS starting in 2021. You've got the IEC, you've got various papers by the IET. Everybody's talking about DC, and DC's been around, not in buildings, but in a lot of other stuff for decades, for industry, for rail. But interestingly, if you want to Google this, a little Google fact, San Francisco Bay Area had the oldest DC power network that operated for 132 years. They only just recently took it out in recent times. So this DC power network, it's a new thing, it's been around for decades and even now over 100 years. So if we go to the next, yeah, I would say one of the things with all of this is we are no longer in an energy crisis. If anybody tells you that, you need to seriously have a look at them, because ultimately we are heading towards a supply and demand crunch. And you only have to look across places like the Netherlands, UK, Germany. You can see all these different and other areas around Europe. You can start to see where they're actually talking about how the energy market's working, and it's all about capacity. But it's not just about capacity, it's about having that capacity at the right time. So as our networks are being sorted out, and there's everyone who's seen Panorama, there's a piece about rewiring the grid in the UK and all the problems associated with that. But we are in the process of changing our grid and changing the way in which we produce energy. And we've literally gone from this in fossil fuel world, which is when I want energy, I just burn some more coal, I burn some more gas, and I get the energy, to this. And we've ripped apart our supply and demand, because renewables will produce energy whenever they want. And to get over some of the humps, sometimes they'll produce more energy in the summer than we actually even need. So energy is not the problem. Yeah, supply and demand, and using it and having it at the same time. So this is one of the really key things to kind of take away, is that our buildings need to respond differently to the network that's going to be there. And in that, there'll be power quality issues associated with remaining at AC that all get swept up. There's efficiency. So when you start to plug this together, you can say potentially you could save on the copper in your building in terms of distribution, somewhere between 40 to 50%. Yeah, because you've got less reduced I2R losses. You can have more efficiency of conversion. So your battery has got a round trip efficiency on it that's quicker and faster. The PV works better. Everything just works better. So you can get somewhere between 20 to 30% energy reduction in your building just by going DC. Yeah. So, and you can then supply and consume it the way you want to do. So it's a new way of designing, and it is what we need to be doing in the future.
Wonderful, thank you. I will hand over to the next question. Maybe, Giel, you want to go over it?
Yeah, of course. Indeed, after like covering the why DC in buildings, the next question that pops up is, okay, how can we actually transition towards DC in buildings? I mean, today these buildings, we're basically used to having an AC electrical infrastructure within buildings. If we say, okay, actually technology, storage, solar generation, electric vehicle charging is actually pushing us towards implementing a DC electrical infrastructure in buildings. How will that transition happen? I mean, because it's not going to be overnight. Today we have AC in buildings and tomorrow we have DC in buildings. And maybe a hybrid solution of an AC and DC microgrid is the way to go. And I want to ask Mame essentially to elaborate a little bit further upon this, on how Vinci Energies and Cegelec see this transition happening.
Hello, everyone. Thank you, Giel, for your question. So, as Adam started to explain it, there's so many reasons why DC is relevant in 2025. So, if we focus on buildings, as Adam said, there's the implementation of EV chargers, but there's also everything that's needed in a building, like LED lighting, LED lightings, the socket, our phone calls, our laptops that are also powered in DC. DC is relevant in IT, data centers, solar panels, wherever we have photovoltaic panels, batteries, and as Giel introduced, EV chargers. So if we see all the environment around us and everything that Adam explained earlier, we can see why DC is relevant. But there's also some reason why we can doubt the implementation of DC, which is maybe the fact that there's some systems that are such as HAV, AC systems, or everything that has motors and legacy equipments that are powered in AC, and for which we now don't have maybe a solution to power them in DC. So that's where the question of how we can implement a DC building or a DC grid in a building makes sense, because we have to find a solution that that helps the two grids to cohabit, and that's why it's interesting what Giel was saying about hybrid systems. You can go to the next slide, Rafael, please. So it's interesting in order to have the best implementation, to choose the right architecture. We can be very happy about DC and think that, yeah, okay, DC is great. We have photovoltaic panels, we have batteries, we have everything that can be in DC. We have, I won't say everything, but so many materials that can be powered in DC. So why can't we go full DC in a building? It's maybe ideal. It's maybe an ideal reflection for new buildings. It would be the best thing for all of us, I think, that are DC fans, to have new buildings in full DC. But maybe it would be a little unrealistic, according if we see that we can have some products or some materials that can be powered in DC, as explained just earlier. So maybe there's two solutions. There's a solution of hybrid distribution, but how can we implement an hybrid distribution? Maybe we can have an architecture of separating AC loads and DC loads. So maybe having two zones, where a zone where we power everything in AC, and another one where we power everything in DC, which is the first, which is the one where we separate AC and DC zones, and also an hybrid system where we have an AC DC converter. And then we centralize everything on a DC bus, which is the one we at Cegelec and Vinci Energies, that's what we did on our demonstrator, because that's what we think is the best solutions. But maybe it can be discussed with everyone later. But we think, and what we think in our point of view, is that an hybrid system is the most realistic actually way to implement DC in buildings. You can
I think I'd add to that, Mame, is that the reason why hybrid is the way to go is there will always be something and somewhere where somebody will say, but what about, I've got this kettle and I want to plug it in. I've got this vacuum cleaner or whatever. So there are things where you need to provide some legacy. But then, as you're saying, is that project specific? It's tailored to the project. It's tailored to the client need. It's the discussion to work out how much and where you can transition. But that gradual transition also enables people to implement without being at fear. Because if you try to, you could probably do a complete DC building tomorrow. But if you did a complete DC building tomorrow, that might be some people were used for it. The client might be used to it, then other people might not really be able to kind of conceptualize that.
Yeah, exactly. Thank you for completing the answer. So actually, of course, there will be challenges for an implementation of a DC, and that's the reason, and that's why current OS is important. That's why having a community built around everyone here, or that's the reason why having a community built around everyone here that can help or give their opinion is important. So we have to, the main challenge would be having a system where the AC and DC grids works efficiently. So that's why it's important to have converters, to have converters, and to try to minimize as much as possible the losses and everything. So that's why it's interesting to have a community like that, so that we can discuss and try to scale up and build something. And that's what we did in our demonstrator. As I explained, it's really an example of an AC and DC system that can work efficiently, because all the energy savings that are promised in DC, we see it in our building. So it's a proof that it can be done, and there's challenges, there's so many things that need to be done for again, but there's a start, and we can all start somewhere and then evolve together. Yes, so just a wrap up for the future of DC in buildings. As I explained and as we discussed with Adam and everyone, an hybrid AC DC is the most practical path forward that we see. The next steps, as I said, is to experiment, to optimize, and to scale up. The key is that a smart integration, and that we discussed it. Having an hybrid AC and DC system does not reduce all the benefits of DC. We still have the energy savings, we still have the reduction of the cable section, we still have the reduction of the amount of cable that are needed. So it's not because we don't have a building in full DC now that DC is not relevant. Having an AC DC hybrid system is very interesting, and we still have all the benefits of DC by doing this.
Great, thank you. We will get back maybe with questions later to you. Now I would like to hand over to Adam for our next question, which is about what is the next question?
So this is really aimed at Avinash is that what's needed to get us to the next level, what's needed to push where we are now, which is in a reasonably experimental phase, and kind of thinking about how things are done, to scaling to which it will be a multi-billion-dollar industry. So as we sort of head off towards the next 5 years, there's a lot of work to do. So the question to you both is what role does the ecosystem and stakeholders play in DC buildings, and some examples of installations. So over to the pair of you, really, and I don't know which one of you wants goes first.
Thank you, Adam.
Avinash, yeah.
Yes. So maybe I can go first, and based on the deck sequence, I'm going. So thanks, Adam, for the question. I missed out on introducing myself. Hello, everyone. I take care of BizDev for Schneider for DC. So far, and we've been in this game for now almost 4 years, and so far, what I feel is what we have put on the bold line on the top. For DC to go forward, ecosystem is the key and partnership is the king. So we have heard a lot, right? Like we are already living in the DC world. Like just look around you, you're using the PCs which are running on DC, you're under the lights which are running on DC, you're driving electric car, which is, as I call it, mobile battery bank. So we are living in the DC world, but let's realize the fact that it is not 100% DC. The topic of hybrid is the dominant here. We are actually living in the DC pockets in the full train. So, and it is not just the players like Schneider, for example, and all the other big equivalents who will make the change. This transition definitely involve all the ecosystem around you, all the players around you, and definitely product is a must. When I say product is a must, for example, load. If there is no load which takes in DC, there is no point in doing a distribution in DC. We will still stay with the pockets of DC in the AC world. Okay, so if there is someone who is innovative, or sometimes I call crazy enough to even think of doing it, there are a lot of questions, maybe not from the individual or the company, but comes around. Why should I do it? When will I have my returns of investment? What is it? Is the game of the power, or it's the game of the energy? Okay, even if I'm convinced that I'm doing it, like how can I design it? Okay, even if I end up designing, like what products can I think about? Like where will I get these products? Where will I research about it? Where will I find them? And imagine one day you even find the product. There are a lot of ecosystem players and various locations which can contribute to you in the products. Then comes the question, who can do it? Like, are the electricians today qualified enough to touch and do and work on DC? Are the norms and standards ready enough? After, even if they have done it, how we will commission it? Imagine we commissioned it. Going forward, how will I maintain and service it? So, given all these questions, and these questions we face day in, day out, people like us, the ones who are speaking in this forum right now, we call ourselves like DC fan boys and girls. We face these questions day in and day out. And this is one of the strong reason why ecosystem is very, very, very important. So after saying this, if we go to the next slide, profile, please.
Coming, yeah, it's a bit, yes.
Okay. So just remembering back the previous slide. So when I say the ecosystem, I'm not only speaking about the products. I'm speaking about the companies that can deliver products for distribution, companies that can deliver designs for distribution, companies that can deliver distribution, companies who will be ready to install and commission, and end of the day, one of the important players are the loads. If I don't have loads, it doesn't make sense. So, and this has helped us, like over the past, with a lot of deployments and installations, we have learned and we are also educating from this experience. Just to give an example, on the right side of the slide, these are all the deployments we have done with DC Systems and Schneider Electric. Okay, and with every installation we have learned. We have onboarded partners, we have educated them, we have educated ourselves. We learned by doing it. In just 2024 alone, we have done 6 installations, and all these installations are current OS based, because this is one platform which is bringing me all those players from the ecosystem that I just spoke about. And thanks to this ecosystem, I'm able to leverage on the partners. And when every project we are doing, it is not only we are educating ourselves, but we are also educating the partners. And that is why it is very important. And this process will not stop. This process has to continue. Learning curve has to be there. It will be there for a couple of years to come. Just going back to the history, good start from Adam. AC took almost 100 years to season out, and we are still learning on AC. And we are just at the tip of an iceberg for the DC world. So that is why I know that there will be a learning curve. It will be some time. The time could be weeks, months, or years. I'm sure it will be faster thanks to the digitization around us. It will be faster than earlier, but We are still learning, and thanks to these partners who are working with us day in, day out from the ecosystem, that we are learning from them, we are educating them, and we are learning from the deployments. Having said that, I request Rafael to move to the next slide. So the topic was like return of experience from a living installation. So in 2024 mid-year, we put up an installation called Solaris in Grenoble, one of our low voltage division's headquarters. And it's a small installation. It's an installation with a 50 kilowatt of utility connection, around 60 kilowatt of photovoltaic. Then there is 6 to 8 EV chargers coming from our partners. We have energy storage, I think close to 300 kilowatt hour. And to deliver this solution, as I was said, like we heavily relied on partnerships. This was not project delivered by one player or two player alone. In this solution, and now we have productized this solution and we are going to the market thanks to the partners like Cegelec, Electronic National. We are able to push it further in the market to give this experience also to others. More than experience, the advantage of doing DC to the others. So this installation, stressing back on this installation itself, you can see on the right, from the current OS ecosystem, we leveraged on the 7 players, 7 partners to realize it. D-Systems and Schneider were the ones who provided products. Cegelec helped us with the installation. We got measuring equipment from Carlo Gavazzi. Innoventum pitched in to do the entire solar carport. Electro International made the entire container with the active front end, with the energy storage, distribution panels. And on top of these 7, there are 5 more players who are yet to join the foundation, but I'm sure they will join one day. 5 more players, which involved maintenance contract people, the permits, the bureau of control, bureau d'études. So there was a lot of learning, and through this learning, we realized the importance of the importance of the role played by the partners. And thanks a lot for that. So left side is a brief snapshot of the system design. We learned a lot from this. We shared the learnings from this to our partners. And now we are a bit more seasoned up to deliver more package solutions like this. This solution is kind of on the verge of getting marketed and available. If any of the people in the chat are interested, don't hesitate to speak about it. Most important is this solution, like when we speak about the advantages, right? You cannot confirm the advantages without realizing, without seeing and measuring that. In this installation, which is running live in Grenoble, we realize the efficiency that we are speaking about. It's around 15%. Again, based on the way we are using, the efficiency also changes. But at max, we are able to realize close to 50% efficiency over the AC installation, equivalent AC installation. And given the reasons that Adam spoke about, it is a clear-cut example of copper optimization by close to 35%. On top of it, very small utility connection. Imagine like we are running this installation with 50 kilowatt connection, and this installation is connected to storage and solar, which is much beyond the connection to the utility. So we are able to realize that. And as I said, I'm hoping that in 2025, we'll realize much more pilots. And with every pilot or project that we realize, we will generate learnings and we will share it with the partners ecosystem and with the current Development Foundation.
Yeah, I think to add to that is that, and I always thought this with the Avinash and the guys, is that 15%, that's about, for depending on the range of your EV car, that's an extra somewhere between 2,000 to 4,000 kilometers a year out of the space. Yeah. So that's what we're saying. We're saying we're getting miles more. I always keep saying it's a bit like the Duracell bunny. If everyone knows what the Duracell bunny is and remembers that kind of, it runs faster and it gets further. So having a DC microgrid for EV gets you further than it does for the same amount of kit. It gets you further in terms of miles in the tank or in the charge.
Yeah, super good point added, because here we are touching base about the advantages, which is not only for the installer, but also for the end user. The efficiency advantage is more for the end user because it's an advantage on energy. So how many kilometers you run or how many kilometers you can do more with the same kind of installation architecture. And then copper is more for installation, but it is actually the indirect indicator of power because I'm able to deliver more power on an existing cross section of copper that I'm potentially able to deliver, or I reduce the copper for the amount of power that is needed to deliver for the system. Thanks for that, Adam. Thank you, everyone. So I let you continue, Giel, from here.
Yes, he prepared some real case example as well, but maybe you want to introduce Direct Energy Partners because maybe the name is famous to the experts, but less famous to the newcomers.
Yes, thank you. Thank you. Indeed, DEP, Direct Energy Partners, actually carries DC in its DNA from day one. Like it's founded by Dusan and myself like 5-6 years ago, early 2020, we founded DEP. And actually today, if you ask like who's DEP, actually DEP is a software provider. We have built a design software platform to design DC microgrids. And we decided to start building that software platform essentially to make the entire design process more productive. Like all the questions that Avinash was raising, like what products can I buy or should I buy? Is it more efficient to do it in DC or AC? Which portions of my system should I run in DC or AC? Should I do a hybrid one? All these type of questions we also faced when we were doing DC projects in the early days of the company. We're both electrical engineers, both Dusan and myself, but we at a certain point said like, if we want to see more DC microgrids out there, we will have to do something about what we call the soft costs. Like all these questions related to product selection, sizing, outweighing the benefits, the disadvantages, the advantages, the uncertainties. Can I get my installation even approved according to the local rules and codes that apply? All these questions take time and effort, and that means that they add to the overall cost of the system. Although the technology is beautiful and yields a lot of advantages in terms of efficiency, reducing the peak capability of your system, there's still a large cost adder in the entire equation of the cost, which is related to the design and engineering process. So that brought us to the point to start converting the knowledge we developed throughout the year into a software platform that we named DCide, and that's DC, Integrated Design Environment. That's the wordplay that we came up with. Everybody is also welcome to give it a try at DCide, dcide.app. You can try it out today. And we built a very user-friendly design environment where you can find, for instance, reference designs for DC system architectures that you can use as a starting point. And we also built a product catalog in the background where you can find all those DC parts that you need, because that's typically question one. I want to look, for instance, for a DC input EV charger. Yes, we know that all chargers internally operate on DC, but where do I go and find, for instance, that Amperenex DC EV charger? We try to come around that, and actually the product catalog is a solution to address one particular aspect of the design and engineering process. So it's built for equipment manufacturers and designers, and it gives them a place to live and interact and get towards a valid system design. Now, I also wanted to share like basically some perspective. So on the next slides, you'll see like one of the two projects like that we conducted over the past years back in the early days of the company. Like a lot of the experience that we code into the software today actually stems from our DC microgrid lab in the US. It's in Charlotte, North Carolina on the East Coast. And that's an installation where there's rooftop PV generation. It's connected to DC EV chargers. It has storage systems of various vendors in there. We have, for instance, LG, we have Savant in there. And we use that lab as a test facility for all this equipment where we test it prior to deploying it with our customers in the early days. But I want to highlight a couple of examples, a couple of advantages essentially of these installations, and especially from more kind of US perspective. Like in Europe, the driver to go towards a DC installation is mostly like reducing the peak capacity of the grid connection that you have. That translates into a direct cost. Efficiency also plays a role, but in terms of the kilowatt hours, like cost-wise, it's typically not making the business case in our case. But if you go to the other side of the ocean, it's like way more oriented towards resilience. It's like making sure that the lights remain on, making sure that I can power my EV charger when the sun is there, but the grid might be out in there. And that's, of course, because of a couple of natural disasters that they experience in certain parts of the country, even parts in California where during the wildfire season, they preventively shut down parts of the grid to prevent spreading fire in the dry season at that point in time. So resilience there is the driver. And I want to make the case for DC for resilience as well, because imagine that you need to build an AC electrical installation today. Your task is to build an AC electrical system today that is capable to island from the existing grid. What you then will have to do as an electrical engineer, you will have to go and find, first of all, transfer switchgear. It's switchgear essentially that basically allows you to connect to the grid or disconnect to the grid. Secondly, you need to add controls and relays on top of that to synchronize your local system with the grid in there. So also the controls to decide when should I disconnect, when should I reconnect. So that adds a lot to the cost and complexity of an islandable AC microgrid. If we compare that to the DC case, actually in the DC case, we technically are islanded already by default. It's like we go from AC, we go through the active front-end inverter, and then we have our DC bus. So imagine the AC grid goes out, essentially as you have storage locally and you have other converters that are capable of making sure the DC voltage remains up. You actually can very easily transition from grid connected to islanding mode without adding a lot of additional equipment on top of that. And that's also where current OS plays a very vital role, in my opinion, because like making sure that your DC bus voltage remains stable, that's something you can accomplish by means of the droop control scheme that's proposed in the current OS protocol. It is a protocol where by means of droop control, and it's a beautiful way of controlling items, where you can, for instance, coordinate between a converter that's connected to the grid and a converter that's connected to a battery. And you basically program a characteristic inside of these converters such that without relying upon any communication between those units, if the grid goes out, the battery converter will automatically step up and make sure that the lights remain on. So that's a very beautiful control concept that's elaborated in the current OS protocol, and that we also apply in our lab and also in another installation. That's the next slide.
Yes, sorry, I don't know where the mouse is gone.
No problem.
Here we are.
So the next slide, that's actually one of the first customer installations we did with the U.S. General Services Administration. So they managed the entire federal building stock in the United States, and they have a facility down in Denver, Colorado. And we basically equipped an entire office floor there, and we took part of the existing PV installation. They were about to replace the inverters anyway, and we used that part of the PV installation to supply, like for instance, the office lights and equipment inside of that building. And I must say, these type of projects also learn you that indeed partnership is key and coordination in there. Because if you compare designing a traditional AC installation versus a DC installation, the traditional AC world is very well known. You call an installer, they bring your cables, they know how to size the wires, they know how to select the protection devices. Done, basically. I mean, not much to it. In this case, you basically have to source your power converters somewhere. You have to procure them. You have to coordinate with the installer. This is how you should connect them. You should layer some controls on top of that. So it's important that all those stakeholders that will play a role in the design and implementation of your system are on board from day one. Even the authorities that at the end of the day come and say, certify, I give you the green light to run the system 24/7 with people inside of that building. Onboard them from day one when you have your first design, such that you can already start educating them about what the installation is about, how it will function, and how you have taken safety measures to make sure that it's safe for people to work inside of this DC environment. It's all possible to build reliable and safe DC systems, but there's also a lot of convincing and education involved in all of these systems. So there's a lot more to it, but I'm gonna stop there. That we have time for questions. So, but at least a couple insights from a practical experience we developed. All right.
Wonderful. Thank you all. Ma'am, I don't know if you want to add a word of conclusion before we move on to the questions about your opinion from Cegelec Vinci Energy point of view.
Yes, so as everyone explained at Cegelec and Vinci Energy globally, we believe in DC. We believe in we're aware of everything that Adam explained that makes DC relevant now, and we're also looking for the solution and how we can implement it. We're trying. That's why we worked with Avinash in Solaris. That's what we did in our project also in Giel, and that's what we're trying to do in other projects. Also trying to work with partners. That's I think that Giel and Avinash really explained it, that we know in current OS and with all the partners that partnership and collaboration is the key. So that's also the importance of Raphael saying, if you want to join us, because we're trying to build a community where we already believe in DC, and we know that DC is important and interesting can be a way to solve some great problems, as Adam explained, but there's also challenges that I presented earlier. So collaboration and also trying, learning, and growing all together. That's I think what we can actually do now. Thank you for your attention.
I think I would also add is that we're now seeing a number of clients come to us, and we're helping them out in their early stages of kind of people who have got problems. That may well be that somebody turns around and says, I want to put 2 meg of solar on top of my roof. I can't put 2 meg of solar on top of my roof because the grid won't let me for the next 5 years. Yeah, we're getting people going, I've got these sort of issues. There's loads of issues coming that actually, when you actually delve in, DC is the answer to that problem. There may be buildings that can't be built because there isn't the power supply and availability to put them where they want them. DC's that answer. So there's multitude of different things that people are starting to wake up now and see where some of these problems. And I think it's because, one, the energy, particularly as we said, from the energy transition of going from fossil fuels to renewables is a completely different energy transition of how we produce energy and how we consume it. and then how our existing infrastructure doesn't actually cut the mustard when it is good enough for this energy transition, and our buildings will have to react to this. Yeah, our buildings will not, even an existing AC building will end up needing to adapt to the infrastructure that it's connected to. So this is a big challenge that I think people are slowly waking up to. But the only way we can solve this is collaboration with loads of different stakeholders. You're not going to get to the moon on your own or Mars. You're going to get to moon or Mars with all your friends around you trying to help you to get there. Not necessarily, if we're not in competition in this instance. Yes, we are in competition when we bid projects, but in this instance, we need to work together to solve this energy transition.
Well said. Avinash, you wanted to have a word? I saw your hand raised. No?
Sorry, I was not raising the hand. I was giving a thumbs up to the
Awesome.
message delivered by Ma'am and Adam. I think they covered very well the entire aspect of it. Time is now if we want to establish this tomorrow. So I encourage all the listeners here and also the ones who will listen the recordings to stand up and reach out in case if they want to know more on this topic.
Mm-hmm. I think also important to know is, like, sometimes it's presented as if there's a battle between AC and DC. And of course, that's history, of course, that kind of pushes there. But if we're fully honest, actually, if you look at the transition that's ahead of us, there's not really a battle. There's not a battle between technologies, storage, solar, EV charging, they will make their way in. We're about to triple our electrical power consumption, triple. So we're about to see the largest infrastructure project that humanity has ever seen in the next 20 years. And then that also implies, I think, that there's also not really a battle between companies, because we're also, I mean, if you look at the workforce that there currently is to develop this entire infrastructure project, it's way too limited today. So there is already a shortage of electrical engineers, installers, all these people that know how to integrate all those systems together. So that's also a shout out and a call out for everybody to collaborate on these projects and get behind this together. I mean, this is the largest infrastructure project that the world has ever seen. So I don't see a lot of competition. I don't see a need for really competition at the end of the day. There's a huge shortage in supply overall.
Wonderful. Over to you, Prashant. Maybe we can start picking some questions from the chat.
Yes, thank you, Rafael. There were one or two questions which I already replied, but I just see now one question from Olga. From which capacity range will be worth to start to think in a microgrid implementation?
Hi. If not others, I can take this question.
Yeah, go ahead, Avinash.
Or maybe I think Adam is better, but maybe I'll start and then
Adam. I can add. I think it's small to large, but you've got to kind of think about this in a staged process and kind of where the technology is and what you can integrate at any given time. So you might have a small system where you've got some street lighting, some PV, some storage, and you can operate that on a small scale at a microgrid level. So, or you might have is, let's say in the future, airport car park charging, tons of it sat around in megawatts. So it's not about necessarily a capacity range. It's about how you take the step process towards where you've got to get to. So you've got to start with something. You've got to start with it being maybe small and manageable, and then working through that process about how you, because as you said, supply chains, there's lots of things that have got to be aligned, because you might be able to get a certain product. And we know that Tridonic make 350 volt DC LED drivers, But the question at the moment is the production line battery that, or the manufacturers, even I will mention Zumtobel as their sister company, they're stamping and putting in the production line a standard AC driver that works off 280 volt DC. So it doesn't work with the same voltage, but you could connect it to 280. So there isn't really anything stopping you. You've just got to kind of break it into chunks and then trying to work out what you can do. The more we all do it together, the more we all trial and work through this, the better it will be. I mean, we've looked at a large scale building for a large scale global client, and they're looking at a 5-10 year transition program. So it's not like they're going, now we're going to go DC tomorrow. They've woke up and said, okay, what do we need to do? How do we prepare ourselves, and how do we create a strategy around to go from, let's say, something small, which it might just be lighting, to mass, large scale megawatts worth of buildings. So as I said, you start small, go big.
Mm-hmm.
Thank you. Maybe just a quick compliment to what Adam said. The first question is regarding the microgrid in general, right? I think I'm taking it as a question which is irrespective of it's an AC or DC. Energy transition is happening fast. Like 2 decades back, photovoltaic was not normal, storage was not normal, EVs were not normal, so DC sources indoors are not normal. As we are heading towards the energy transition, consumers are becoming producer, and that is why the introduction of the term prosumers. When the complexity on this prosumer installation increases, that is where there is a sense of need of having microgrid increases. So that is where, so it's, as he said, like, it's not really the capacity question, it is what I want to do with my installation. Second is, another question becomes like, which places should I focus with DC? This again question could be answered by what is the footprint of my DC loads in the installation or sources in the installation, right? Like if I have too many high-speed chargers or low-speed chargers, if I have too many drivers, too much of installation of BESS and photovoltaic, there it starts to make sense to leverage upon a DC microgrid. And that is where, as we were saying, that the ecosystem plays a key role, because you need to find products. It doesn't make sense to do DC if you don't have a DC product, right? Like Tridonic has a LED driver. If there is no LED driver, you cannot have a DC lighting installation. So there are more players coming in, yes. And the footprint of DC is increasing in the building, yes. And that is when it starts to make sense to have this as a complement to the existing ecosystem of AC, like what Giel said, instead of having a battle in front of them. Thank you.
Thank you. Thank you, both of you, for the response. I see a hand raised from Kobat Shafi. Sorry if I pronounce your name wrong, but you can open your mic and ask.
Yes, good afternoon. Do you hear me?
Yes.
Good afternoon, Kobat Shafi from TU Delft. Actually, I have been doing research on microgrids for over a decade, mostly on modeling stability and control, mostly on AC side, but I've been doing some work on DC as well. So I have 2 questions. Thanks, by the way, for this interesting webinar and for the organization. So I have 2 questions. The first one, you mentioned that you have been taking droop control into account. So my question is that, of course, it's simple, it's communication free, and it works simply. So that's the only control, let's say, method that you have been using for implementation of, DC microgrids and DC systems up to now. This is the first question. And my second question is about, from your point of view, what is the open questions, open research questions you may have for, let's say, researchers to work on it? Of course, from our point of view, we see some research directions, but from, let's say, practical point of view, which research directions do you see, or which research questions exist so that researchers from universities, from academia can work on that directions? And what kind of collaboration do you see between, open Open OS? No. Current OS or your company for corporations? Thank you very much.
So on the installations, sorry, I need to ask others if anyone wants to go ahead.
You can go first, Avinash. I have a couple.
So with respect to installations, Kubad, as you're coming from TU Delft, I can tell you comfortably that the Pulse building in TU Delft is running comfortably on DC. In Netherlands itself, close to you, there is also N470 installation, which is also running on DC. So out of the many installations that we have done through DC systems, there are many of them which are running purely on droop control comfortably for a long time. After that, are you achieving the max out of the droop control? Probably not. You need to keep changing the settings of the sources based on the ecosystem, the weather, for example, right? There is a topic of weather prediction. There is the topic of peak shifting based on all the elements around. So there is an element of smartness needed on top. I agree, but can the system run stably just on droop? The answer is yes. It is, it is actually, if you can drive to Alsmere, we have our DC headquarters here, DC systems, where there is a space of around 600 meters square, which is running without an EMS, just on the droop.
Of course, with some steady state errors and voltage drops, right?
Yeah, sorry? I would like. Sorry, carry on.
Sorry, I didn't get
go ahead.
I would like to kind of throw a bit of a designer's head in this and say we haven't yet got to the scale in built environment level that shows that actually works on a 500 meter bus, as an example. And then the question is where do you stuff your loads in and out? And how do those loads work? Conceptually, a bus is completely different to the vast majority of the way in which we design electrical engineering. So everybody's used to stream distribution from the transmission and distribution, from the LV networks, from HV networks in buildings. It's all stream distribution, and you stuff your load in at the point where the stream can go back downhill again. So you don't take a megawatt of PV and try to bung it in the end. Yeah, you always take it back to where it's comfortable to stick a megawatt of PV in. So I think whilst we've got installations and proved that the bus does work and the bus is stable, I'm very nervous about whether when you scale, yeah, that actually works. So I think you've got one of the bits of research is when we scale to something of a larger size, and do we put in, so as an arbitrary thing, this is and kind of lots of different stuff, is to say, well, actually, conceptually, in an AC world, I take a megawatt of PV, group it together and stuff it in where I need to stuff it in. But actually on a bus now, I could take 200 kilowatt lumps and stuff them in wherever I want to stuff them in, which is way, way better. But then the question comes is, what does that do to all the droop control and the stability of the network, and how's that managed? So I think there is a number of questions that I've got and the team I work with got, that we always are going in the current OS when we talk to people at OS, and sometimes there's like everyone's got a different opinion because they've got a different view of the world. So we need to take those views of the world, from designers to contractors to O&M people to facilities to everybody's got a slightly different view, and we need to pull that experience together to actually understand what we're doing. Because yes, we can do it, but my question is, when we scale to a larger size, does scaling to a larger size open up an issue which we will solve? There is no way we're not going to solve it, but it just does it all of a sudden do something. Oh, we never thought we were going to do that in the world ever in the world.
Yeah, true. I actually want to echo what Adam just said. Indeed, like droop control in principle, indeed, should work also for larger systems. Like basically you set for your loads, generator, storage systems, you define power versus voltage essentially. But then the next question becomes like, if I now add up all these curves, I factoring also the voltage drops across the wires that I have, will there be a stable operating point of my entire installation? Essentially, if you sum up all the generation at a certain voltage level and all the loads at a certain voltage level, is there like a zero crossing if I add up all these droop control curves together? So I think that's a very actual and useful research subject that's also very active within the current OS committees. Like it's a current question, like how should we configure these droop control curves in there to make sure that at all times there's a stable operating point guaranteed. And at all times that also implies different network configurations, because at a certain point, a certain converter might be in maintenance, or a certain part of your system got isolated from the rest because of a fault in that particular section of the system. So you got to be able to evaluate your robustness of your system given all these droop control curves, and you might need to make a couple of adjustments to these curves to make sure at all times you reach a stable operating point. It's possible, but it's how to evaluate, how to configure that.
And then if you layer on actually how we deliver projects on a day-to-day basis, we then need to be able to put a set of rules and guidance around that so people can replicate. So actually, because that's the other problem is at the moment, it's electrical engineers that are happy being uncomfortable and enjoy playing to make sure they can deliver the projects. But that's not the future for scale. The future for scale is making sure we can actually give us rule set of guidance that said at the beginning, when you've got everything and it connects in like this, this is how you size your bus. And if you move your load around on the network, you size it slightly differently. And if you do this, so all those things need to be kind of mapped out for people so that they actually, so it's easier and replicable. At the moment, it's people that are very happy being uncomfortable and understanding what they need to do, because it's all achievable and it's all solvable. We're not trying to do rocket science or anything, but we need to be able to replicate this for people and make it easier and more digestible.
Thank you very much for your answer. Yeah, actually, it was quite interesting to discuss on this. And yes, actually, we noticed the same, let's say, research question, and it's interesting that from your point of view, you also see this as a challenge. Thank you very much.
Thank you, everyone. We are 4 minutes on top of the hour, so we can close this session. If you have any questions, further questions, do not hesitate to contact us. We are present on LinkedIn. We have a YouTube channel also, so follow us on LinkedIn and YouTube. You can contact us on the email address below. You can also contact us through our website, currentos.org. And if you have any projects to do not hesitate to reach out, and we can connect you to the partners to execute and develop the projects.
And also, if you're interested in joining, let us know, because we need more people, more different points of view. We want more people to help with this development, because we'll only succeed if we do it together.
Even have to do marketing. You see, partners are or ambassadors.
I can say it's really worthwhile joining from our perspective of Jacobs. We've learned a lot. We've kind of moved with our understanding, and it's helping us massively on our journey. So definitely, and you get to speak to some very interesting people from all walks of the industry. So definitely worth joining.
Thank you. Thank you to all the speakers.